So great. So I'll begin by defining two problems and then we'll understand various definitions in the context of those two problems. The first is vertex cover, where as input we are given a graph G and an integer K. The goal is to check if there exists a vertex cover of size at most K in G. By that what we mean is check if there exists a vertex subset of size at most K such that if you look at any edge in the graph, then at least one of the endpoints of that edge is in the set S, is in the set X, and this holds for every edge. Okay, such that for all edge UV in the graph, U belongs to X or V belongs to X, or it could happen that both of them are in X. Okay, but at least one of them is in the set X. So this will be our first problem that we'll be interested in. The second is CNF SAT. For that I'll build the language a bit. So consider a variable set Z. Okay, so it's a finite set of variables. Say Z is equal to Z1, Z2 and so on up to Zn. N is the number of variables. And now let me define what literals are. So literals are nothing but a variable in its true form or its negated form. Okay, which means that suppose for instance a variable in its true or in its negated form. For example, Z1 is a literal, okay, and the negation we'll denote it by this symbol. Negation of Z1 is also a literal, okay. Z2 is a literal. Negation of Z2 is also a literal, and so on. Okay, so we have a variable in its true form, or this is the negated form of the variable. The symbol denotes negation. Okay. So now let me define what a clause is. A clause is nothing but an OR of literals. Okay, so it's an OR of literals. For example, Z1 or not of Z2 or Zn is a clause. Okay, so this symbol, V like symbol is OR symbol. This symbol is negation symbol. Okay, so an OR over a set of literals is a clause. Now let's understand what a CNF formula is. A CNF formula is AND of clauses. Okay, it's an AND of clauses. For example, Z1 or not of Z2 and say 2 or not of Zn or not of or Zn minus 1. This is a CNF formula. I can add more such clauses, for instance say Z1 or Z2 or Z3 and so on. This is a CNF formula where it is an AND over a bunch of clauses, finitely many. Okay. So now let me define what a D. Yes. Sorry. Okay, sure. So do you know what a graph is? So you know it. A graph is nothing but is a pair V comma E. V is a finite set, and for our purposes it's a finite set, and E is a subset of V cross V of distinct vertices. Okay. So now we are given a graph G and an integer K, and the goal is to check if there is a subset of the given graph, so that the size of the subset is at most k. And if you look at any element from the edge set of the graph, this, then at least one endpoint of this edge is in the set X. Okay. So now let me define a DCNF formula, which is nothing but a CNF formula where every clause has at most D literals. Okay. Consider an integer D. So I'll write maybe DCNF formula here. Yes. Please. A CNF formula where each clause has at most D literals. For example, this is, can you give a bound on D? Like, can you say this is some DCNF formulas for some D? 3, right? This is a 3 CNF formula. However, if I add here not of say Z4, then it will no longer be a 3 CNF formula, but it will become a 4 CNF formula. So now let me define. So since we have limited board space, I hope these notations are clear to you. Okay, and maybe I'll define the DCNF formula here so that I have the 2 problems that we are interested in on this side of the board. Okay, so let me define, before that, let me say what we mean by satisfaction of a given CNF formula. Okay, so an assignment, a Boolean assignment, is nothing but a function from the variable set to 0, 1. Each variable is assigned exactly one of the 2 values, 0 or 1. And we say that an assignment F satisfies a given a CNF formula phi. Any guesses when? It evaluates to 1, which means that you substitute the values. So instead of Z1, you write what F of Z1 is. Instead of Z2, you write what F of Z2 is, but now there is a negation. So if it is a 1, you flip it. Okay, you make it 0. And if it is 0, you flip it and make it 1. Okay. So an assignment satisfies a CNF formula phi if for each clause C, which is say L1 or L2 and so on up to or LQ, LIs are literals, at least one of the literals is set to 1 by F. Okay. So what do we mean by a literal is set to 1? If the literal is the variable itself, then so it's a variable Z, then F of Z should be 1. However, if the literal is say not of Z, then Z should be 0, which means that not of Z is 1. Okay, negation of Z is 1. Okay. So in the DCNF problem, DSAT problem, I'll directly define DSAT. As an input, we are given a DCNF formula phi, and the goal is to check if there is an assignment that satisfies the given CNF formula. Okay, so the goal is to check if there exists a satisfying an assignment satisfying phi. Here I want only Boolean assignments. Okay, assignments of the form that sets each variable to 0 or 1, exactly one of the values 0 or 1. So we'll keep these 2 problems on the side, and we'll understand all the other definitions that we'll see shortly in the context of these. Are these definitions clear, everyone? So I can erase this part. We will only have these 2 pieces. Okay, fine with everyone? So how many of you have heard the term NP completeness or NP hardness? NP? Okay, a very few of you. Okay. So let me begin by defining So we here, if you look at these two problems, I'm not asking you to compute anything. I'm just asking you to check if certain thing happens or not. Okay, so it's kind of a decision version. Either such a set exists or not. The decision is Boolean. Either it's true or it is false, right? Either there exists such a set or not. Either there exists such an assignment or not. Okay. So let me formally define decision problems. Okay. Actually, it's same as, so if you know basic things about computers, you might know computers understand only 0 and 1. Everything is written using the two symbols 0 and 1, right? So for us, for instance, if we speak English, the letters that we understand is A to Z, capital caps and small letters, right? However, the computer understands only these two symbols. Okay, so everything must be presented to a computer in as a string, which is represented using the two symbols. Okay, so a decision problem is not, and sigma star is set of all strings over the set 0, 1. Okay, strings which have symbols only 0 or 1. For instance, 0, this belongs to sigma star. Okay, these are finite length strings, not infinite length strings. Okay, sigma star is the set of all finite strings where the symbols are only 0 or 1. Okay, so now what a decision problem is, a decision problem is nothing but L subset of sigma star. Okay, now let's understand, we define these problems, vertex cover, DSAT, now in some English language, right? Now how do we define a decision problem in terms that a computer understands it? Okay, in the language of computers. So let's try to do that. So here, any guesses? How do you encode vertex cover in this format? So suppose I want to define, so this is also a decision problem, right? I'm asking you to decide. I'm asking you to check whether such a set exists or not, right? So how do you phrase it as a decision problem in terms of this language? Okay, so let us look at a string. So notice that if you are presenting a graph and a number k to the computer, it will again be presented as a string, right? It will be presented as a sequence of zeros and ones. Okay, so suppose you have a string s. This does not represent a pair of a graph and an integer. Okay, suppose this string, you have already fixed an encoding scheme on how you represent your graph and how you represent numbers. Okay, in that scheme, suppose a string s over 0, 1 does not represent a pair which is a graph and a number, then such a string should not belong to L. Okay, suppose we are defining L as the vertex cover in terms of sigma star. Okay, so in which case it will not belong to vertex cover. Now let us look at those strings that represent a pair of graph and a number k. Okay, so now let us look at strings that actually represent a graph g and a number k. Okay, so now the string s will belong to the language of vertex cover in this notation of sigma star. Any guesses when? If and only if G has such a set of size at most k. Okay, which means that there exists. So S is your G comma k, some graph comma k. If and only if there exists X subset of VG, size of X is at most k, such that for all edge UV in the graph, U belongs to X or V belongs to X. Okay. So for those strings that represent a pair of graph and a number k, it is in my language of vertex cover, which is Same as saying that for all those graph and number k which form yes instance of the problem for which the answer is yes, okay, they are in my language of vertex cover, otherwise they are. Okay, so we can reinterpret this problem defined in English language in terms of sigma star in this fashion. Okay, that's how decision problems are defined. Analogously, you can interpret D sat in this language, in this notation. Okay, so now we have understood this. Sorry, size of X, the number of elements in the set X. Okay. Okay. So now that we understand this, we'll move further and we will talk about decision problems. Okay, we'll gradually come to the notions of NP hardness, NP, the class NP, and so on. So I hope now you understand what decision problems are. So I'll erase this. So these two will be important throughout. So I'll keep them. So let us now understand the notion of the class NP. Okay, so you might know the class P, which is those problems for which, now we are talking only about decision problems. Okay, those decision problems for which there is a polynomial time algorithm. So what we mean by an algorithm for a decision problem, let's take a moment and first understand that for a problem, now I can use it as a subset of sigma star, right? For a problem, say A, we have an algorithm. If given a string S, which is subset of which belongs to sigma star, we have an algorithm A. If given this fancy A correctly decides if the string is in the language or not. Okay, in time bounded by some function f of which only depends on the length of the given string. Okay, so there is such an algorithm, and this function f is called as the running time of that algorithm. When f is a polynomial function, then it's a polynomial time algorithm. Okay, this is what we mean by an algorithm for a decision problem. So there is a function f and there is an algorithm A that given a string in sigma star correctly decides whether S is in my language or not in time bounded by f of the length of it. Okay, then we say that it's actually also called as decidable. Okay, and whenever f is a polynomial function, then we say that such a problem is in the class P, polynomial time solvable problems. You might have encountered polynomial time solvable problems, several of them. For now, we will understand something beyond the class P, okay, which is our class NP. So NP stands for, any guesses? Sorry? Non-deterministic polynomial. It is not polynomial, but it is non-deterministic polynomial for reasons I'll not get into, but it stands for non-deterministic polynomial. Okay, so the problems that I have written this on this half of the board are really hard problems. Okay, finding a polynomial time algorithm for these problems are major and the most central open problem in the field of computer science. Okay, we do not know any such algorithms, and we do not believe that such an algorithm exists, but that is just our belief. Okay, we do not know it for sure. But it's not terrible. Okay, not terrible in the following sense. Okay, can you, if I give you this set X somehow, okay, if your friend says that, look, they have managed to compute a set X which is a vertex cover. Okay, they are claiming that it's such a set X is called as a vertex cover. Okay, vertex cover of G which satisfies this property. Okay, so suppose your friend tells you that X is a vertex cover, but you should not believe your friend, right? It's a really hard problem. So believing somebody just because they are saying it is not good. So let's see if we can verify it ourselves. And note that it is quite easy. So if your friend says they are given a graph G and a number K, and they give you a set X and claim that look, X is in fact a vertex cover for G of size at most. Okay? Let's take a step back. If your friend is given a graph G and a number K and they're claiming that no, it's a yes instance of a problem, which means that this belongs to the language of vertex cover. Why should you trust your friend? Okay? The point is then you don't have to like completely disregard the information that your friend is giving. You can ask, why do you feel so? Okay, give me a proof that in fact G comma K is a yes instance of the problem, which means that G comma K as a pair belongs to the language of vertex cover. In which case, you can ask your friend to give such a set X, right? Such a set X, notice that checking whether size of a set is at most K is very easy. That you can do it in polynomial time because it's polynomial in the size of the graph. If the graph has n vertices, size of X could only be at most n. Right, which means that you can check if the size of the set X is at most K or not. K will be at most n, right? And you can also check, you can go over each of the edges in the graph and check if at least one of the endpoint is in the set or not. This you can do it easily in polynomial time, which means that given if someone gives you the answer, gives you this set as a certificate, look, I am claiming that this is a yes instance, but here is a proof for it. Then you can verify such a proof easily. Okay, this is the essence of the problems that are in the class NP, which leads us to the definition of efficient verification. Okay, so to define the class NP, I'll define what we mean by efficient verification. Okay. So, an algorithm A is an efficient verifier for a problem A. So, deliberately I am writing this as a fancy A to denote it's an algorithm for this problem A, which is supposed to be subset of sigma star decision problem. Okay. So fancy A is an efficient verifier for problem A if the following conditions hold. Okay. Firstly, this algorithm now not just takes the string, not just if you look at A as your vertex cover problem, it not only takes a graph and a number K, but also it asks to give you the set X. It will only check whether X is satisfying these conditions or not. So it takes two strings. Okay. So A takes two input strings S comma T in sigma star. Okay. So this S is supposed to denote the pair G comma K, and this T, roughly speaking, is supposed to denote such a vertex subset X. Okay. That is like the mapping. Now, what is this algorithm A supposed to do? It takes two inputs, and there is a, so here it's a polynomial time algorithm. Anyway, I'll write it. It's okay. So there is a polynomial function Pn such that for any S in sigma star, okay, imagine S has the pair G comma K, okay, for any given string, S is in the language, is in the decision problem that we are considering, if and only if there exists a small witness that certifies that in fact it's a yes instance of the problem, and which can be verified by using this algorithm A in polynomial time. So I asked for such a set, right? Here it is simple. You have to check whether the set has size at most K or not, and you have to check this condition, right? But if the conditions are more complicated, it is not even clear if you can check these conditions in polynomial time, correct? So we want that you should be able to check the proof in polynomial time. This string T is a certificate or a proof for S being in the language, okay? So which means that a string is in my language if and only if there exists a string t, if and only if there exists another string t in sigma star. Okay, so note this. Just a minute. Okay, this t is given to me as a proof. Okay, there should exist a short proof, which is this t. There exists this where the length of t, okay, the length of the string t is at most pn. It's only polynomial. It's of polynomial length. If the proof itself, the certificate itself is really huge, at least you have to read the whole certificate, in which case you cannot hope to have a polynomial time algorithm, and we would like A to run in polynomial time. Okay, roughly in the length of S alone, because we are demanding that T should also be polynomial by this. Okay, which is of polynomial length, says that if you give both S and T to your algorithm, then it outputs yes. Okay. Okay, so for instance, let us understand it in terms of vertex cover. We have already understood how I can define vertex cover as a subset of sigma star. Okay, that we have understood. Now, what is this algorithm A? A verifier. It's nothing but it takes S, which is a graph G and a number K, and it takes T, which is a vertex subset. What it needs to do is it needs to check these two conditions. Okay, so notice that vertex cover in fact has such an efficient verifier. Okay, so all the decision problems which have here A runs in must run in polynomial time. This is also an important condition. Okay, A is a polynomial time algorithm. I have not defined NP yet. Okay, so this I was defining NP efficient verification. I'll come to the class NP. Okay, here I'm not asking you to solve the problem. I'm asking you, here is the instance of the problem. Here is my proof that in fact it's a yes instance of problem. Can you verify my proof? That's all I'm asking. It's like the difference is if you are taking an exam, okay, say a written test. You are solving the question and a teaching assistant evaluating it. So what we are trying to say here is evaluation is easier than actually coming up with the solution. That's the essence. Okay, like once someone has written the whole solution, I can go line by line and see if each of the statements are correct or not. Okay, the one follows from the other or not, and it's the same essence that given a proof I can verify it in polynomial time if it is correct or not. But coming up a proof itself is more non-trivial task. Okay. So now the class NP is all those decision problems that admit efficient that have efficient verification. Okay, that is the class NP. All decision problems that admit efficient verification. Okay, so now I have defined the class NP, and now we will look at actually an algorithm design paradigm, okay, which is called as the reduction. Okay, which will help us obtain even more structure in the class NP. But more generally, so if this is clear, I'll erase it. Okay, so more generally, the reduction is a technique, a way to design new algorithms. Okay, in addition to it giving other useful properties. So we will understand what a reduction is. So consider two decision problems. Okay, so I'll consider two decision problems A, B. Okay, we say that there is a polynomial time, there is a polynomial time reduction from A to B denoted by B if something happens. Okay, so there is a polynomial time reduction from problem A to problem B, which is denoted by the symbol A less than equal to subscript PB if there exists, if. So let's first try to understand the essence, okay, of what it is saying. We want to say that if somehow someone gives you an algorithm for problem B, okay, gives you a polynomial time algorithm for problem B, I can design a polynomial time algorithm for problem A. Okay, that is what it is saying. So so this less than equal to symbol with this letter P stands for polynomial time. Okay, we are saying that if you look at the polynomial time computations and polynomial time algorithms, B is substantially harder problem than A, which means that if you manage to design a polynomial time algorithm for B, then you already have a polynomial time algorithm for A. Okay, so with respect to polynomial time solvability, B seems at least as hard as problem. Okay, so we say that there is a polynomial time reduction from A to B if given, this is given, okay, polynomial time algorithm for A, for B, we can find polynomial time algorithm for the problem A. Okay, so this is what a reduction is. We'll also understand it in the problems that, in terms of the problems that we have defined. Okay, we'll see a reduction shortly. Fine. So what we'll use this definition and we will use B as our vertex cover. Okay, and we'll use A as our. In fact, we will use, instead of D, we will use just 3 sat. Okay, so note that D was a number, right, where each, a 3 CNF formula is a CNF formula where each clause has at most 3 literals. Okay, so we will take our problem A as 3 sat. Okay, so given a polynomial time algorithm for vertex cover, we'll try to design a polynomial time algorithm for 3 sat. Okay, that's what we'll do. So I'll erase this and I'll write the goal. Yes? Sorry? Yes, actually all problems or anything that computer solves, you actually turn it into 3 sat. Okay, it's that versatile. Every problem that you solve is turned into an instance of 3 sat, more generally CNF sat. Every. That's how computers work. Okay? And yes, vertex cover has a lot of applications. It's one of the very classical problems for which has been extensively studied in the literature. These are decision problems. I mean, we are taking decision problems here. The reduction itself, the notion of reduction extends beyond decision problems, but for the purposes of this short lecture, we will just focus on A and B being both decision problems. Okay? And the class NP we define only for decision problems. Okay, there is a reason for that, because it actually captures the essence of hardness of the problem. Okay, I'll leave it as just a remark. Yes. 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 We will be proving it. Yeah. Okay. So now this is the definition of reduction, and now we will try to take A and B as 3 sat and vertex cover respectively, and I will prove the statement. Okay. This will give us a polynomial time reduction from 3 sat to vertex cover. Okay. So now I'll assume I'm given an algorithm for vertex cover. Using this algorithm, I will now find an algorithm for 3 sat that runs in polynomial time. Okay. So my A is VSAT, B is vertex cover, and we have an algorithm B for vertex cover. Okay, this is a polytime algorithm. Okay, so I'm equipped with, someone has already written the code form. Okay, so I'm given such access to such an algorithm B for vertex cover that runs in polynomial time. Now I will design a polynomial time algorithm for 3-SAT. That's the code. Okay. So what we'll do is, so notice that we will try to turn an instance of 3-SAT to an instance of vertex cover. Okay, that's what we'll do. So just for simplicity and simplicity in explaining, we'll assume that each clause has exactly 3 literals. That's not very crucial. Actually, you can modify the reduction and a bit and make sure that whatever we are assuming is not a big deal. But for the purposes of the explanation, let's suppose each of the clauses in phi have exactly 3 literals. So what I'll do is, so let us look at an instance phi of 3-SAT. Note my goal is to resolve a given instance of 3-SAT. So at my hand I am given this phi, okay, which is a 3CNF formula, and I have to report yes or no. Yes if there exists such a satisfying assignment, and no otherwise. Okay, so now I would turn this phi into an instance of vertex cover. Okay, and now for the created instance I will run the algorithm B for the vertex cover. Okay, that's the code. Okay, and somehow I would like to use the answer given by the vertex cover algorithm to create my own answer for this. Okay, so we'll do the following. So suppose here we have phi has variable set z. Okay, the variables are z1, z2, and so on up to zn. Okay, and we have clauses. Okay, so phi is a CNF formula over this variable set z. Okay, phi is a 3CNF formula. So what I do is I create an edge each for each of my variables. Okay, so this edge, the one endpoint will be for the literal z1 and the other will be for literal not of z1. So I do this for every variable. Okay, so this, let me mark it by z1 not of z1. This is z2 not of z2, z3 not of z3, zi not of zi, zn not of zn. Okay, so this I have done for, so what I am creating, given this CNF formula, I would like to create a graph G and a number K. I want to create an instance of vertex cover, and I would like to use this algorithm that is given to me on this created instance and use the answer for this instance to somehow find the answer for phi. Okay, that's what we are trying to do. So I have somehow encoded this variables. So what is the essence is, so the goal here is, so whenever I set my variable z, say z1, if I set it to 1, I would interpret in this graph as selecting the vertex z1. This is just interpretation purposes, okay, for you to understand. The graph, I mean the algorithm itself will use none of these, but for you to understand, imagine if a variable, say z1 is set to true, is set to 1, you choose the vertex z1. So note that we have created n many edges in the graph, and for every edge we have to choose at least one endpoint, which means that from each of these edges you need to, any vertex cover will have to select at least one of the endpoints, right? So we are encoding all possible assignments to the variables in the following way. Okay, if you set a variable to, so if you set a variable zi to 0, then interpret as selecting not of z1 in your vertex cover. Okay, if you set it to 1, you interpret this vertex zi being in the vertex cover. That's your interpretation. This way you can encode all possible assignments to the variables to the set 0, 1 in this graph. Just this much. We have not yet encoded any clauses. We are just saying that now we have a way to interpret assignments in terms of a vertex cover. Okay, now let's bring, so now we have to do something with the clauses, so let's bring them into picture. Okay, so the idea will be for every clause I'll create a triangle. Okay, so the property that I'll be using is, so suppose let's look at an example of a clause. C, which is say Z1 or Z2 or not of Z3. Okay, this is a clause which has 3 literals. What I'll do is, I know that if I have a yes instance, at least one of these literals is set to true. Say Z2 is set to true. Okay, which means that Z2 is must be set to 1. Okay, so what I'll do is, I want to encode this choice of selecting how the clause is satisfied, which literal satisfies the clause. Maybe it's satisfied by many literals, but choose just one which satisfies the literal. Okay, so independent of the assignment, let me try to encode how I can make a choice of like choosing one literal to satisfy this clause. For this, I will insert a triangle. Okay, so suppose this is a clause C. Okay, so I create a triangle whose vertices are WC1 for the, let me write the exact literal itself. Okay, for the clause C and for the literal Z1 appearing in this clause, I insert a vertex. Okay, for the clause C and the literal Z2 appearing in the clause, I create a vertex. For the clause C and the literal Z3 not of Z3 appearing in this clause, I create a vertex. Okay, so in this process, I have created 3. So if phi has m clauses, I will create 3m many new vertices. Okay, 2n vertices I have already created, and for every clause I create 3 new vertices. Okay, and I make them a triangle. So for each clause I will have such a triangle. Okay, so now let me explain the connection. How do these variable vertices versus the clause vertices interact? Okay, so the point is, so note that if you have a triangle in the graph, any vertex cover must choose at least 2 of the vertices, because if I choose only one, so say if I choose only one and I do not choose the other 2, then this edge will not be covered. So any vertex cover must necessarily choose at least 2 vertices from a triangle. Okay, this is the property that I'll use. Okay, so suppose you end up selecting these 2, then somehow I will use this to enforce that. So this, the vertex that I leave, that I do not choose in my vertex cover, this will be the literal that needs to satisfy the clause. Okay, so what I'll do to this end is, I will add an edge between every such literal, okay, literal vertex to the corresponding variable, literal vertex. Okay, so for instance, let's see the construction for this example. So if the clause is this one, I will add, from here I add an S to Z1, from here I add an S to Z2, and this is not of Z3, right? So I connect it to Z3. So notice that, so this I do for all the clauses. Okay, this I have explained just for a fixed clause as an example. Now you do exactly the same thing for each of the clauses and construct your graph. Okay, so that's the construction of your graph G, and I set the number K to be, any guesses what should I set? So note that I am setting the budget too tight. So N, I need to select one from each of these edges that I inserted for the variable, the literals. Okay, 2 for each of these triangles, and that's all I allow. So notice that if G has a vertex cover of size this much, it is only allowed to select at least 2 from, it must select exactly 2 from each of the triangles. It must select exactly 1 from each of the edges on the top. Okay, and that's it. That's all the budget it has. Okay, fine. Is the construction clear? So we'll quickly wrap up the reduction. So Pranav, 10 minutes, right? Yeah. Okay. So we'll prove that phi has a satisfying assignment if and only if this graph G comma K is yes instance of the vertex cover. That's our goal. Okay. So now maybe I can erase this part now that we are comfortable with the definitions. So we will prove that. So note that this graph itself you can construct in polynomial time. Correct? This integer itself you can construct in polynomial time. So this whole construction, your computer can do it in polynomial time. You can write a code that does this construction for you in polynomial time. And now, once your algorithm has done this construction, it will make a call to this algorithm B for this graph and for this number. Okay, so what we'll prove now is P is a yes instance of 3 sat, which means that it admits a satisfying assignment if and only if G comma K is a yes instance of vertex cover, which means that G has a vertex cover of size at most. Okay, so let's look at the forward direction. Say phi has a satisfying assignment f from z to 0, okay. Now let me construct a vertex cover. Okay, so the vertex cover X will be as follows. So firstly, for each of these edges that I added for variables, I'll insert exactly one vertex. Okay, so in X, for each Z in the variable set, if f of z equals to 1, add z to X, else add naught of z to X. Okay, so what I've done is, so suppose Z1 was set to 1, this was set to say 0, okay, then here I'll add Z1 in my set X, here I'll add naught of Z2 to my set X. Okay, so note that for each of these edges I have included exactly one of the endpoints. Okay, so I have exhausted my budget N. Okay, so now since phi is in fact satisfied by this assignment, we know that for every clause there exists a literal which is set to true. Okay, so what I do is I choose exactly one such literal and include the other 2 endpoints in my vertex cover. Okay, so now what I do is, let's see where I can write. Maybe I'll write, so the clause C was Z1 or Z2 or not of Z3. So what I do is, for each clause C, which is say L1 or L2 or L3, okay, say f of L1 is true, is 1, okay. So if the literal for 1 is satisfied, what I do is add WCL2 and WCL3 to the set X, okay. So suppose Z1 was set to 1, which means that this clause is already satisfied, right? So I don't insert this but I insert the other 2 endpoints. So for every clause I have a triangle, and from every such triangle I have inserted exactly 2 vertices, right? So the edges which are drawn on the top and the triangle edges are already covered. We only need to cover these edges, correct? Okay, fine. So now notice that any edge which is incident to this endpoint, a selected endpoint, is already covered. So if you look at this particular edge, right, if this endpoint is selected, then we don't have to include the other endpoint, because I mean it's already covered, right? Now let's worry about an edge of this form. So notice that when can we have such an edge? Notice that in this case, this clause was in fact satisfied by this literal, right? And so in this example, the clause was satisfied by Z1 because Z was set to true, which means that this was already selected in the vertex cover, in the set X. That's how we have constructed, right? Which means that even all these edges are covered. Okay, so this proves forward direction, which is if phi has a satisfying assignment, then G comma K is a yes instance of the vertex cover. Okay, now let's look at the other direction, which is also very similar. Just you have to now look at from the vertex cover point of view. Okay, so let us look at the other direction. Say G comma K is a yes instance of vertex cover, okay, which means that there is X subset of VG, size of X is at most K, where X is a vertex cover of G, which means that each edge has at least one endpoint. what I do is, so k is recall, it is exactly n plus 2m. So now let me come back to my picture. So now I'll construct a satisfying assignment f. Okay. So now given this set x, let me construct my satisfying assignment f from z to 0, 1. Okay. So if for z in z, so note that from each of these edges, exactly one endpoint can be in the vertex cover. Why? Because of the budget. The size of x can be at most n plus 2m. For each of these edges, I need to choose one. For each of these triangles, I need to choose 2. So 2m plus n is already gone, which means that nothing more can be chosen. Okay. So for each variable z in z, either, so if z belongs to the set x, set f of z equals to 1, and if z, otherwise not of z must be in x, right, belongs to x, then set f of z equals to 0, which means that not of z is set to true. Okay. So notice that all these top edges are covered because for every variable I have included at least the literal vertex or the true the variable, the vertex which is in true form. Okay. For every triangle, let's see why. So now what I want to prove is that f is a satisfying assignment, right? Okay. So let's look at a clause. Okay. Let us look at some clause of this form. Okay. So say in this clause, 2 of the endpoints. So now we will worry about this assignment because now we have a vertex cover. Okay. Say this triangle is present in the graph, which means that this set x must have chosen two of the vertices. Say the vertices that are selected is this vertex and this vertex. And this is not selected because from every triangle we can select at most 2. And we need to select exactly 2. So this is left out. Okay. But now notice that this set x is a vertex cover, right? Which means that the other endpoint must have been in the vertex cover, right? So this is an x, this is an x, this is not an x, which means that this must be in x. What does this mean? Not of z3 is in x. So not of a variable is in x, which means that the variable must have been set to 0, which means that this clause is satisfied by not of z3. Okay, so that's how you can prove that the other endpoint, since it's a vertex cover, must have been in the vertex cover. So the assignment that we have constructed satisfies all the clauses. Okay, so note that your algorithm for 3-sat is fairly straightforward. You construct this instance g comma k and call the algorithm for it, and whatever answer you call the algorithm b on the created instance. If it returns yes, you also return yes. If it returns no, you also return no. Okay, and that's it. Okay, so we have seen a polynomial time reduction from 3-sat to vertex cover. Okay. So this reduction is also the notion of reduction lies at the crux of the definition of NP hard problems, which are the hardest problems in the class NP. In fact, 3-sat is something called as NP complete. I'll briefly state and conclude what we mean by this. So whenever we say that, let me define NP hard first, okay? So what we mean by the class of problems, which is NP hard problems. These are those problems so a decision actually does not need to be a decision, but for now, since we have only seen decision problems, I'll state it this way. Decision problem A is NP hard if for every problem, so let me write it as B, you'll see in a minute, okay? We say that a problem B is NP hard if for every problem A that belongs to the class NP, the class NP of problems, we have a polynomial time reduction from A to B, okay? So it's not even clear why such problem should exist, but it exists, okay? And a problem is NP complete. B is NP complete if 1, the problem itself is in NP, and second, B is NP hard. Okay? And there is a result which says that the Cook-Levin theorem, a modified version of it, which says that 3 sat is NP complete. Is it visible, the theorem statement? So this is Cook adaptation, okay, of Cook-Levin theorem, which says that 3 sat is NP complete problem, which is the hardest problems in the class NP, which means that if you have a polynomial time algorithm for 3 sat, then you have a polynomial time algorithm for every problem in the class NP. Okay, and notice that we showed that you can take, so forget about the other thing. We showed that we have a reduction from 3 sat, a polynomial time reduction from 3 sat to vertex cover. And we have also showed that vertex cover is in NP, right? We have at least understood. So notice that this also means that, just try it as an exercise, that vertex cover must also be NP complete. Okay, try it as an exercise. And yeah, that's all I have to say. I'll stop here.
Yeah, so we saw that this problem is NP hard, right? So what is this problem? Just to remind you, there will be some graph. A graph consists of some vertices, right, and some edges. Right? So an edge is a pair of vertices. You want to select a minimum sized subset of vertices that will hit every edge. That is to say, every edge will have one endpoint in that minimum size subset. Right? So finding such a minimum, well, what we saw was that given a graph G and an integer K, right, is there a vertex cover of size at most K? So deciding this is NP hard, right, or actually it will be NP complete. Which means that in practice we do not have any efficient algorithm to solve this. Right? So if somebody gives you a graph and asks, is there a vertex cover of size K? So then you cannot really give them an answer. Right? But on the other hand, so this problem we just stated it like combinatorially, but this shows up, or similar types of problems show up in many places. Right? Even that CNF SAT that you saw, that will show up in many places in many applications, like say software verification, things like that. So one way or another, we have to like figure out how to solve these problems. So I mean, we have to make some sort of say compromise in some sense, right? So what kind of compromise we make? Well, this is a yes/no question, so there is not much room for any compromise here. Either the answer is yes or no, right? And you have only two choices. So what we will do is that we will move from here to this optimization version of the problem, which is to say, like, which was how problems are normally stated, which is that given this graph G, find the minimum vertex cover of this graph. Right? Instead of saying, is there a vertex cover of size at most K, which becomes a yes/no question, here the question is, what is the size of the smallest vertex cover of this graph? I mean, it's the same question as you can see. It's just that the way question is stated, the objective becomes different. Right? This time the output given a graph G is a number. Right? So obviously you cannot find that number efficiently using an algorithm, right? Because it's NP hard. If you could find it efficiently, then obviously you will be able to answer this question, and so you will be done. And you have solved an NP hard problem efficiently. It cannot happen. So what you do is that you slightly relax the question. Right? So you say, I'm giving you this graph G. Now give me a vertex cover which is not much larger than the minimum vertex cover. Right? Like give me, so I can ask you to give me the smallest vertex cover, or I can ask you to give me something that is not much larger than the smallest vertex cover. Let's say at most 10 times the smallest vertex cover. Now that's a very different question, right? That question can be efficiently solved. It's only finding the smallest vertex cover that is hard. Finding a slightly larger vertex cover for a graph is not hard. In fact, we will see how we can do that very easily. Right? So this leads you to this notion of approximation algorithms. So can anyone guess how we should state this approximation question for vertex cover? Any ideas? So what do we want? The objective is, or let me write goal rather, shorter word. Find a vertex cover, let me call it X, of G such that size of X is at most some alpha times size of, let me call it X star, where X star is the smallest vertex cover of G. Here alpha is some number, right? So this alpha can be 5, this alpha can be 10, this alpha can be 1.01, right? Anything. So can alpha be 1 in this question? Do you expect? I can set alpha to be 1, right? But if I set alpha to be 1, then do you think that would I be able to answer that question efficiently? Right. But if alpha is 1.01, then it might be possible. Okay. So for this lecture, we will set alpha equals to 2 for this vertex cover. So this alpha is called the approximation factor, because I'm trying to find a solution which is X, right? Which is not the optimum solution, it's not the smallest solution, but it is maybe here alpha is 2, so alpha times larger than the optimum solution, right? So I'm trying to find a solution which is sort of not the best, but approximately the best. And the degree of approximation is controlled by alpha, right? As long as I can find a solution which is, I mean, between the optimum and twice the optimum or alpha times the optimum, I'm happy. And this question can be solved quite easily for vertex cover. So how do you think we can do this? Any suggestions? So what is, let's recall, what is vertex cover? Can you speak a little louder? Every edge? No. So you want to find a set of vertices. It's not colored chalk here, I guess. Let's say I take this vertex. Hopefully you can see the graph I've drawn here, right? Just make the edges. So if I take this vertex and this vertex, I think that, is that a vertex cover of the graph? Is there some edge which is not covered yet? Huh? Every edge is covered. So it turns out, I mean, this is sort of a simple graph, so it was easy to find. But anyways, this is an example of a vertex cover. So if you look at these two vertices, any edge in the graph has one endpoint in either here or there. So that's, therefore these two vertices, they are a vertex cover of this graph. For a more complicated graph, it will be a much larger set, which will be more difficult to find. Now, so what do we want to do, right? We want to pick vertices such that every edge is incident on one of the vertices, right? and we want to find the smallest set of this size. So let's look at, so what would be the simplest thing to do here? Take all the vertices, but that could be very large. Here, even if you take all the vertices, I think it's what, 3 times the optimum. Right? So that's, I mean, that's a valid solution. But that's not the solution we want. So what could be a slightly better way? Half of the vertices. But how do you select which half? I cannot hear you. Breadth first search. How will you use breadth first search? Okay, you start from this vertex. What if I start from this vertex then? No, I mean, how will you select the vertices into vertex cover? That's what I'm asking. You will not select that because this has only one edge. What if I select this vertex? It has 2 edges. But if you select this, then what would be the size of the? You want to select these guys only. Yeah, but I mean, you have to give me a procedure which selects this guy over that guy, right? What would be the rule? Highest degree. Okay, so that's a valid statement. That look at the graph, look at the vertex with the highest degree, take that into your vertex cover. Okay, and then so now, okay, so let me just complete what you were saying. So you take the vertex with the highest degree, like there could be multiple such vertices. So here there are 2 such vertices actually. So you take this one, right? That is one valid way to select this vertex. After that, you delete this vertex and every edge that is incident on this vertex, because all those edges have been covered. Right? And then what do? Then you look at the rest of the graph and again select the highest degree vertex. Okay, so that is a valid way of constructing a solution. You keep doing this until there are no edges left, right? Question is, what would be the approximation factor of this solution? Because somehow you have to compare the size of the solution you computed with the size of the smallest optimum solution. Right? So how will you do that? Okay, so let me tell you something. And this one I don't quite remember, but there is an example which shows that if you use this highest degree rule to construct a solution, then there is an example where the size of the optimum solution is something, and the size of this solution computed by this rule is like some log. So if the graph has n vertices, then log n times that minimum thing, which is clearly not what we want here. So you can actually construct this example. I'll think about it. If I have the time, I'll try to do it. I don't recall it right now. Right? But highest degree rule is a valid way to construct a approximately the same solution. It will run in polynomial time, obviously, and all that. But it does not give us what we want, right? Which is that the approximation factor is 2. The approximation factor of that solution will be log n. Log n. N is the number of vertices in the graph. Right? So the approximation factor need not be a constant number. It can also be something that depends on the size of the input. Right? So okay. So any other simple thing that you can think of? Okay, so let me just tell you. So what do we want to do, right? So let's take one edge of the graph. So what do we know about this edge? So there are these 2 endpoints of this edge, right? And in any vertex cover, at least one of the 2 endpoints must be there. So why don't I just take both the endpoints? Pick an edge, take both endpoints of that edge, put it in your vertex cover. Now you have taken these 2 vertices in the vertex cover, which possibly would have covered a bunch of other edges as well. Right? So if I take, say, this edge, there's a tiny green chalk, so let me use that. So I take this vertex and this vertex, the endpoints of this edge. Once I do that, Well, this edge is definitely covered, like in fact twice over. But these other edges are also covered, right? This edge, uh, this edge, these three other edges are also covered, right? Because one of their endpoints is in these two vertices that you picked. So let's delete, these two vertices and all the edges that are incident on one of these two vertices. Right? The graph has become slightly smaller, just like your greedy reduction rule. And then in the remaining graph, I find another edge, do the same thing. Find another edge, do the same thing. This will also eventually lead me to a vertex cover. Yeah. So now can you argue that the approximation factor of this will be 2? Yeah. Right. Right. So let me just restate what you're saying, I think. So that how did we construct our solution? So we picked some edge, we took both the endpoints of this edge and deleted all the edges that are incident on either of these two endpoints. In the remaining graph, I took another edge and deleted every edge that is also incident on one of these two endpoints. Then I took another edge, did the same thing. I kept doing that until I ran out of edges in the graph. Right? The graph has no edges left. So this was my solution. Now, what would be the size of the optimum solution if you had picked some, I don't know, some say p edges in this process, right? You did this process p times before the graph had no edges left. Right? So now, what is the size of the solution that you have computed? It's 2 times p, right? Because you picked p edges and for each edge you pick both the endpoints. So the size of this x that you computed, that is 2p. But what would be, you have to compare the size of x with the size of the optimum solution. So what would be the size of that optimum solution? Can you say something? Why? Okay, so yeah, you're right. So let me just make it more formal. So you have these edges that you picked, right? These p edges. Notice something about these p edges. If you take this edge and any of the other edges, they have no common endpoints. Right? So for this edge, I had to pick either this endpoint or that endpoint, at least one of the two. But neither of those endpoints will cover any of the other edges, any of the other p minus n edges. And this is true for any edge in this collection. So every edge in this collection will require a distinct vertex to cover it. Right? So therefore, my optimum solution will need at least p vertices. It could be more, but it will need at least p vertices. So therefore, I can say that this is at least p, whereas that is the size is 2p, which I can also say is at most 2p. So size of x is at most 2p, well exactly 2p. Size of x star is at least p, right? And this is true no matter what the graph is. It is always the case. Therefore, here the alpha should be 2. Right? So it's a very simple algorithm. So this is an example of an approximation algorithm. Right? So this is a very simple algorithm which gives you a 2 approximation for vertex cover. Right? Now, here are some things that I'm just telling you, which we will not go into. Turns out that this is the best possible. You cannot give, well, we strongly believe because of various reasons, mathematical reasons, that there is no other approximation algorithm which will give you a better than 2 approximation and also run in polynomial time. Right? So there is no way that you can basically if you manage to beat this, then that would be like a very big result in some sense. Yeah, so this approximation algorithm is one way to solve these very difficult problems. Now they do not directly apply to many problems like this CNF SAT. It is unclear what the notion of approximation should be, right? Because CNF SAT says give me a setting of the variables to true or false such that the formula evaluates to true. Right? Now it's like, what is approximately true? There is no meaning of that, right? You can try to create some meaning by saying, give me a assignment of the variables to true or false, such that let's say at least 50% of the clauses are true. Right? So that is not called CNF set, that is a different problem which is called max set. Right? Okay, let's look at max set briefly. I think that's also easy enough. Let me write down. Right, so given a, let me say 3 CNF SAT formula, right? So let's call that phi, right? Which is some clause, another clause, some m clauses on n variables, where each clause is essentially like 3 literals, right? This or this or this, right? Where, yeah, I mean, you just like it was what Akanksha was talking about. So, given this formula, find an assignment of the variables so that you satisfy a maximum number of clauses here. Right? So that version is called max sat. Right? Well, max 3 sat, because these clauses have length 3. So this is why 3 sat. So can you think of a simple algorithm which maybe satisfies so the perfect solution would be that you can satisfy all the things. Right? Can you think of a simple algorithm that satisfies maybe half the things? Okay, that is valid. The issue will be that once you start to analyze this, it'll not be that difficult, but it will require some effort. Let me give you a much simpler algorithm. A simpler algorithm is simply this: take any variable, randomly set it to true or false. Yeah, just do that. So, what is the probability that this particular clause is satisfied? There are three literals in that clause. I mean, each literal is either a variable or negation of a variable. So if I randomly set a particular variable to true or false, I mean, its negation will also be randomly set to true or false. Right? So when is this clause satisfied? When at least one, yeah, you're right. I'll just expand on it. So when at least one of the literals is true, right? Each literal can be true or false with probability half, and there are 3 of them. So the probability that this clause is not satisfied is when all of them are false, which happens with probability 1 over 8. So the probability that this satisfies is at least 7 over 8. So probability some Ci is satisfied is at least 7 by 8. Now, there are all these other clauses, right? So what can we say? What would be the expected number of satisfied clauses? Yeah, which is much larger than 50% actually. Right? So why is it okay? So that's a different type of question. So, but here is a very simple way that randomly set some of these variables to true or false, and this will lead you to a approximately optimal solution. Like, I mean, a solution where 7 by 8 fraction of the clauses are satisfied, right? Which is like much larger than 50%. So the thing is that this procedure will also work for 4 CNF, 5 CNF, any CNF. It's just that as the clauses become longer and longer, the probability will become smaller and smaller, right? And at some point, it will hit 50%. So you can always guarantee that at least half the clauses will be satisfied. No, it's 7 by 8 times, it's like m times 7 by 8 is the expected number of clauses that are satisfied. Right? Number of variables is n. M could be much larger than n. Right? Okay, so this was one method, which is, as I said, it's called approximation algorithm. So you take your problem, you make sure it's a optimization problem where you are supposed to find a solution of some minimum size. So the output is essentially a number, right, which indicates the size of the solution. And then your goal becomes that I don't find a solution which is, the best number possible, but some approximation to that best number. Right? So sometimes for vertex cover it is 2, for 3 CNF set it's 7 by 8. Well, because, okay, so here is another thing. Vertex cover, right, it was a minimization problem. Find the smallest vertex cover. So therefore, when I find an approximate solution, that is going to be larger than the smallest vertex cover, right? So the approximation factor was 2, which is that our algorithm gave us a solution which is twice as large as the smallest vertex cover. So this is a minimization problem. This maxat is a maximization problem. I want to come up with the assignment to the variable so that as many clauses as possible are satisfied. A maximum number of clauses are satisfied, right? Now, this here we want to find a solution, like as the solution, basically you want to find the largest number, right? So therefore, maybe it is possible that there is an assignment that satisfies this formula. So all m clauses will be satisfied, right? But the solution we are finding that is satisfying a smaller number. Right? So here you could say that number of satisfied clauses, right? It's at least 7 by 8 times best possible. Right? So, okay, here I should also clarify that I sort of assumed that none of these clauses are sort of like opposites of each other and things like that, but that's not not a big deal. Okay, so this is a maximization problem. The best solution is to maybe satisfy all of them or the largest possible fraction of them. So what we are guaranteeing is that our solution will satisfy at least 7 by 8 of them. So the approximation factor for a maximization problem, you can either state it as 7 by 8 or you can also call it 8 by 7. Right? Sometimes if somebody says that the approximation factor for a maximization problem is 2 or 5, what they mean is that the solution computed is at least half as large or 1/5 as large as the optimum solution. Right? I mean, just don't get confused by this. But in both cases, whether minimization or maximization, you have this approximation factor, and somehow you have to establish that this approximation factor is something by some argument. So over there, we use the idea that the edges we select, they're completely disjoint. Therefore, the optimum solution is at least half the size of what we are computing. Here we use the idea that, well, probabilistically, there's a very good chance that a clause would be satisfied. So on expectation, at least those many would be satisfied. And then this was a randomized algorithm which you can de-randomize by various other methods. So you can make it completely randomized. Okay, so this is one notion of how you handle NP-hard problems, right? So one other thing I should mention, which we will not go into, is that so these things I stated sort of combinatorially, right? Here it was pick some edges like this, there set some things randomly. But all these problems, most of the time, are solved using these so-called linear programming methods, right? So you write down an LP for the problem, and then you solve that LP, and then you find some clever way of rounding that LP to a solution. And along the way, you also argue using some structural properties that that solution has a good approximation factor. So this is one method. So, I should not have erased this. Let's look at another method, right? So while they were introducing us, I don't know if you recall, so he mentioned a word called parameterized complexity. So that is essentially another method of solving NP-hard problems. Okay? So let me explain how that works. So once again, so we are sort of back to the decision version. You're given a graph, you're given an integer k, you want to decide if there is a vertex cover of size k in this graph. Right? Parameterized complexity directly attacks this problem, and it tries to solve this problem in a running time which is like some function of k and polynomial in the size of the graph. So normal polynomial time algorithms, right, which we call efficient algorithms, they will run only in this much time. This is not there, right? Like maybe BFS or maximum matching, their running time is just some polynomial in this thing. It could be a small polynomial, large polynomial, but they're polynomial. Here we are looking for algorithms whose running time is not completely polynomial. It is mostly polynomial, but there is also a factor that depends only on k. Right? So this is some function of k, typically an exponential function, let's say some c raised to k. where C is some number. Right? So if the K is a much smaller number compared to G, so you have a very large graph, but you want to find a very small vertex cover in it. So then this algorithm runs, in a reasonable amount of time. It's slower than polynomial, but it is still very, very efficient. Right? So for problems like vertex cover or other problems where you come up with this sort of an algorithms, these are called fixed parameter tractable algorithm, and this whole area is called parameterized algorithms. Right? So you take your input, you think of your input as the main input instance and a number which is your parameter, and your running time of the algorithm should be a function of the parameter, possibly exponential function, but polynomial in the rest of the input. So what would be a simple, so let me draw that example again, or maybe a different example. Right? So this is your graph. You are asked, is there a vertex cover of some size k in this graph? Right? What would be a very natural way of doing this? And notice that here the solution you will find will be the optimum solution, or at least a solution of size at most k. Right? It's no longer allowed to find a slightly larger solution. So what would be the best approach of doing this? Or any approach. Like suppose I just give you this graph, how will you decide if the graph is a solution of size k or not? What would be the obvious thing? Yes. Brute force way would be just look at all subsets of vertices of size at most k and check if it is a vertex cover. If any of those subset is a vertex cover, you answer yes. Otherwise, the answer is no. It's a inefficient. So how much time does that algorithm take? Yeah, so there are n vertices. You're looking at subsets of size k, right? All possible subsets of size 1 up to k. So therefore, the running time of this algorithm is proportional to, say, sum of I from 1 to k and choose I, right? Which will be approximately n raised to k. Yeah? So if k is sufficiently large, that will approximately be 2 raised to n. But I mean, even if that is not the case, the running time for any k is typically something like this. Whereas we would like something like this. So any ideas on how we can maybe do that? So because we are in this lecture and we want to finish it quickly, so surely it cannot be that difficult, right? I mean, you can also use that as your so it's similar to what we did for the approximation algorithm, but in a slightly different way. Okay. So what you do is, once again, you select some edge. What do we know about this edge? We know that at least one of its two endpoints will go into the solution. Right? So why don't I just branch? Right? So I picked some edge. Right? So in this branch, I pick u. Let's say this is u, this is v, the two endpoints. I pick u into my solution. In this branch, I take v into my solution. Then the graph is g minus u, and here the graph is g minus v. I mean, I delete this vertex u and all the edges that are incident on u. Right? So at least in both these branches, this edge is taken care of. Right? And I know that the optimum solution will either take u or v. Right? So one of the two branches is the correct one. It could potentially take both of them. So then both these branches are correct. Because I have taken u, that doesn't mean I cannot take v sometime later in this process. Right? Because of some other reason. So if the solution contains u, then I can go down this branch and I will be correct. Right? And then in this branch, I will pick some edge again. Like again, split into two directions. I'll keep doing this. Right? Eventually, I would have branched on one edge, two edge, three edge, and so on, up to some k edges. Right? If at that point, my set of choices, right, I have made k choices, does not lead to a solution, then I'm convinced that that particular sequence of choices is not going to give me a solution of size k. But that is only one of the sequences, right, which is like this. Like if you think of the branching as a tree which is branching into two, right? So this is a binary tree. Right? So one of these paths from the root to the leaf did not lead to a solution. But there are other paths. And in fact, I go and explore each of those paths. Right? So if there is a solution of size k, one of those paths will lead me to the solution. Why? Because, I mean, suppose I magically knew that solution, then that solution contains one of the endpoints of this edge. So I take that endpoint. Now, after that, there is this another edge, and the solution has, say, that is some PQ. So either P or Q is in the solution. So whichever one is there, I go and follow that branch. So if I keep following this, looking at the solution on the edge, and keep following the path from root to leaf, I should eventually arrive at that root, that bottommost path, which corresponds to the solution I was magically having. Right? So I will recover the same solution which was there. So if there is a solution, it is somewhere there in this tree, and I just have to go and look through each of the bottommost leaves of the tree to find out where it is. Right? How many leaves are there in this tree? Yeah, it's 2 power k, because I mean there are k levels of this binary tree. Right? So it's a binary tree. Each vertex has 2 children, and that vertex has 2 children, and so on. And the height of this tree is k. So the number of leaves in this tree is 2 power k. So in fact, the number of leaves of this tree is 2 power k, but if you have to, because you also went through all the internal nodes, those will be roughly another 2 power k. So total is like 2 times 2 power k. And all other steps at any of these points, that is polynomial. So therefore, this factor here becomes 2 power k plus 1, and this remains polynomial. We have to like go and find an edge, and so on, so forth. All these steps, other things, those are polynomial. So here is a very simple algorithm that, given a graph G and an integer k, run in 2 power k plus 1 times some small polynomial in n, and decide if there is a solution of size k or not. Right? What if the selected edge will not work? Why will it not work? Let me come down to you. Yeah. See, so the choice of the edge for the first edge, right? That can be any edge in the graph. A vertex cover is supposed to contain endpoints, vertices that cover every edge. So if I take any edge of the graph, then there has to be something in the vertex cover that covers this edge, right? I just branch on which that thing is. So there is no wrong choice for the first edge or any of the edges at any of the stages. Yeah, yeah. They have to cover all edges. Right? That is the reason it works. So I can choose anything here. It is completely arbitrary. So the only thing is that when you choose this second edge, it should have nothing like, because I've chosen something and deleted that chosen vertex. The second edge that I select, that is not incident on anything selected earlier. So therefore it is correct. If you selected an edge that was already hit, that could lead you to a wrong solution. Right? If this edge was already, one of the endpoints was already present in the vertices selected up till this point, that would be an incorrect choice. But we already delete them, right? After every choice, I delete whatever edges were already covered. So therefore, the chance of that happening is 0. Yeah. So this is a very simple example of what we call a FPT algorithm for vertex cover. So the running time of this algorithm is slower than polynomial, but depending on the solution size, it could be very, very fast actually. So on like a large computer, say k equals to 100 is not really a big deal. It can easily take care of it. So this is for vertex cover. What about, say, that max 3 sat we saw? Any suggestions for what we can do there? So what was max 3 sat? It was you were given a formula which had various clauses, right? And you have to satisfy a maximum number of such clauses, some Cm. Each clause was made up of some literal, which I'll write as, say, xi, or sorry, or xj or xk, right? So this xj, xk, they could be a variable or the negation of a variable, right? So this is what each clause looks like. So what would be a way uh, to ensure? So the first question would be, what is my k in this problem? Right? I should have clarified that. Let's look at it like this. Suppose that instead of max sat, let's say we are looking for a different solution. We want what is called as min once sat. Right? So this is a slight variant of the 3 sat thing. Once again, you have the CNF sat formula, 3 CNF sat. You either want to decide if there is a setting of the variables. So variables are set to true or false, right? But is there a setting of the variables where at most k variables are set to true? That satisfies this formula, right? So I mean, true corresponds to 1, false corresponds to 0, like in a computer. So min ones 3 sat means the number of ones or the number of true variables that should be there is limited or minimized. So here we ask, is there a setting of the variables where at most k variables are set to true and the formula is satisfied? So here, given this version of the problem, I can set k to be the maximum number of true variables, right? So can you think of a algorithm in this case similar to that? So here, note that we have to satisfy all the clauses, just like we have to cover all the vertices. It is 3 sat now. It's min once 3 sat. Right? Correct. Same algorithm. Take this clause. I have to satisfy this clause. Right? So yeah, then I have to choose one of the variables to satisfy. Then I have to decide, which variable I set to true. Right? Doing that may keep some variable, something as true or false. Sorry, which literal I set to true. Doing that may set somebody to true or false in the variable set. Right? And then that will have an effect on the other clauses that also include literals of those variables. Right? So you make a choice, then that cascades and so on and so forth. Because you know that this clause has to be satisfied no matter what the solution is. So therefore, one of the branching choices, there are 3 ways of going about it. One of those choices is correct, right, if there is a solution. And so you explore all 3 choices and then 3 other choices and 3 other choices and so on. And at some point, you would have set some like too many variables to true, and at that point you stop. But there is a complication here, which is that setting a literal to true is not the same as setting a variable to true. Right? So you have to do some other work here to make that thing happen. So there is some complication there. If k is small, what you may or may not arrive at a solution, right? You don't know. The vertex cover, yeah, so there can be a graph where there is no solution of size k. So in that case, if you will not find a solution in any of the branching leaves, right, in that branching tree. So then you say there is no solution. Right? Because if there is a solution, then there is one which you have found. Right? Because you could have traced the path that the solution would have taken like this. Yeah, so I think basically we just wanted to show you, these are the methods by which people try to solve these NP-hard problems. All of these variants of SAT are NP-hard and so on and so forth. You can give further reductions essentially like that. So I guess the reduction from 3 SAT to max 3 SAT is sort of obvious. The reduction from that to min once 3 SAT is probably not so obvious, but it is still doable. If you are interested, you can check it out. And similarly, if you go and look at any textbook on approximation or parameterized algorithms, right, you will find more and more sophisticated techniques and things. So this is basically what people like. This is a large chunk of research in algorithms these days. Because these sort of problems, right, like vertex cover, or so if you look at any real world application of computational problems, almost all the time the problem will turn out to be NP hard. So you have no choice but to try and solve them one way or another. Right? Sometimes you need an optimum solution. Approximation solution is not good enough. So then you're willing to invest in some computing power. So you use this FPT algorithm. It costs you some computing power because of this factor, but it's a bounded amount. Or you are happy with the approximate solution, but you just need it fast. So then you try approximation algorithms. So, like the research essentially focuses on coming up with better and better algorithms, like maybe make the algorithm faster, or improve the approximation factor, or various other things. And so that is what we do essentially. Right? So this workshop, the idea was that we just give you a glimpse of these things. Right? So as you can see, not all, like most, like it's not true that all these algorithms some super fancy things. They're based on some very simple combinatorics, but the idea is that somehow you relate the solution or whatever you compute to the size of an optimum solution. Right? One way or another, you sort of capture it cleverly using these arguments. Whether you capture it in the branching tree or in that selection of these p edges that you had made, which were completely disjoint, you just have to realize the underlying property of what the solution looks like, how I can lower bound the size of the solution or something like that, or upper bound the size of the optimum solution, and then relate it to the solution that you computed. Yeah. So this was all we sort of wanted to do. So thank you for coming to this workshop. I guess it went on for a bit longer period of time. So any questions that you guys may have? Okay, so the landscape is a little more complicated than that. So yeah, so there is this class of problems which is called P, which are efficiently solvable. You will find the optimum solution in polynomial time. There are these problems which are NP, non-deterministic polynomial time. So they are not expected to have efficient algorithms, although we still cannot prove that. And what we know about these NP hard problems, or NP complete problems, is that they're all related to each other. If you solve one of these problems, because of those reductions that you saw, right? So they all can be, like vertex cover can be converted into another NP hard problem by some reduction in polynomial time. So if you can solve that problem, you can solve vertex cover, right? And consequently, you can solve every other NP complete problem. Right? So it's essentially there are like thousands of problems which are now known to be NP complete. Right? But we don't know how to efficiently solve any one of them. And if we could solve one of them, we will be able to solve all of them. So this sort of leads us to believe that they're not going to be solved efficiently. Right? So that answer is more complicated. So we don't know how to prove how that can be done. But funnily enough, we can prove that various techniques that we have cannot prove that it cannot be done. So yeah, so like I don't want to go there and confuse you, because that is also not something I work on, right? But it is a fairly difficult problem. Plus, like NP and P are just two classes of problems. There are problems even more harder than NP, right? There are problems which are between NP and P. A famous example is graph isomorphism. Right? Like given two graphs, are they the same graph? Right? It's not clear whether it's not in NP, that is known, but it's also not known to be in P. Right? So there are various problems which sit in between. No, so for example, graph isomorphism, I think the best algorithm right now is some which. So if you have two graphs of size n, then the running time is some n raised to log n, or something like that. Right? So this is very different from, say, solving vertex cover optimally, which for various reasons we believe will take time, which is like 2 raised to n. Right? So n raised to log n is actually like 2 raised to log square n. Right? So I mean that looks like a larger number, but actually that is much smaller than this. Yeah, the 2 raised to, like, log square n is much smaller than n. Right? So yeah, so problems are sort of stratified by amount of time they require to solve, and we place some problems in between other problems and so on and so forth. So actually, like, there are many other classes. These are called complexity classes. Right? So NP is a complexity class, P is a complexity class. there are these other, like there are various other things. So if you're interested in complexity, for example, you can pick up a textbook and sort of see an overview. Right? So here, the only thing we considered was sort of the running time. Right? Another factor that comes out is how much space does my algorithm use. Turns out most of the algorithms here use polynomial space. The amount of extra information I have to store for that branching tree or that set of edges, it's not much. It's polynomial in the size of the input. But there are problems where the amount of space required could become exponential in the size of the input. Right? So then there is a definition of complexity classes using how much space you need. Right? So we saw a randomized algorithm for this max 3 set, right? So there are some problems like given a polynomial, right? That polynomial, if you completely simplify that polynomial, it could become 0. I mean, I can give you a polynomial as like multiplication of various things, right? It could be a very complicated thing. If you completely solve this thing, either it will turn out to be a polynomial which is sum of a bunch of things, or everything will cancel out and it becomes 0. Right? So right now we don't know how to. So if I give you a polynomial as a product of a bunch of things, how can we like tell you whether it's 0 or not without using randomization? The process simply is that randomly set these variables in the polynomial to true or false. If it, to some random numbers, not true or false. If the evaluation of that polynomial comes out to be non-zero, then say that the polynomial is actually a non-zero polynomial. If it comes out to be 0, then of course you say it's a 0. Right? So this is a randomized algorithm. We don't know of any deterministic algorithm, like without using randomness, to solve this. So it's a randomized algorithm which takes polynomial time, right? But we don't know how to convert that algorithm into a non-randomized algorithm also taking polynomial time, right? So a lot of people work on this, right? How can I take this very basic problem and solve it in polynomial time without randomness? I mean, so there are a lot of these more and more strange details that come out as you take closer and closer look at problems. And yeah, so this is why you have so many people doing all these things, which like at a first glance may not seem like maybe a lot.